My name is John Zittel. I'm the co-chair of the City of Bath Climate Action Commission. On behalf of our commission and the Kennebec Estuary Land Trust and the Patten Free Library, who are all co-sponsors of this Climate Conversations series, I'd like to thank you all for coming. Truth in advertising. I am not a climate scientist, but I've been tracking the technical literature on climate change for about 40 years. And this evening, I'd like to try to just give you a little bit of an overview of the science that goes into our thinking about climate change. And before I start going into any of the details, I'd like to ask two questions. I'm not going to be able to see your hands when you raise them for any responses, but the first question is, how many of you believe that human activities are a factor in changes in the climate that we're seeing? Okay. My second question is, the premier group in the world that assembles information about the findings that the scientific community has made is the Intergovernmental Panel on Climate Change. They issue a report every few years. Those reports typically run several thousand pages long. How many of you have read one of those reports? Oh, I actually see a hand. Good. That's great. No worries. I heard exactly those same questions asked at a meeting a few months ago in a room full of Nobel laureates. And the response was just about exactly what we got here. And so that's okay. What I want to do tonight is talk with you a little bit about the science. But as I go along, I'll try to also talk with you a little bit about the question of why do we trust science, and how, without having read a several thousand page report, how can you have confidence in the results that are coming out of the climate change community? So with that as background, let's start talking about climate change. The basic idea that we want to talk about is very simple and straightforward. It's the greenhouse effect. You've all been in a greenhouse. You've all observed what happens, even if you're not completely clear on why it happens. Visible light from the sun shines through that transparent glass in the greenhouse, and it warms things up inside the greenhouse. That warmth gets trapped in the greenhouse because even though the glass is transparent to visible light, it's not transparent to the heat energy that's re-radiated from the plants, the tables, what have you, which that heat shines in the infrared, and glass absorbs in the infrared. It's not transparent. So exactly the same thing happens with the Earth. The atmosphere and the gases that make up the atmosphere form a layer around the Earth that serve exactly the same purposes that glass in a greenhouse does. And some of the gases that are in the atmosphere serve to trap heat with the Earth in exactly the same way that the glass around a greenhouse traps heat within the greenhouse. And a certain amount of that is good. The estimates from the climate community are that if we did not have greenhouse gases in the atmosphere, the average temperature on Earth would be right around 0 degrees Fahrenheit. So some amount of greenhouse warming is good, but too much of anything can be too much. So what I'd like to do is start out by telling you a little bit about the history and remind you that science is a cumulative process. It builds on the work of lots of individual researchers, each building on the researcher that came before them. So I think it's useful to understand a little bit about that sequence of events and how long and how much difficulty was involved in getting down those basic ideas of the atmosphere acting in the same way that the glass on a greenhouse acts. So a little bit of a history. First of all, In 1856, an American by the name of Eunice Foote reported to the American Association on the Advancement of Science. And she reported on some results that she had made in the laboratory, where she had determined that carbon dioxide could actually act as a greenhouse gas. That is, she saw that carbon dioxide was certainly transparent to visible light, but she saw that it absorbed heat. And she speculated a little bit about whether that might have some effect on the Earth and on climate, but she was really working just on that very basic question. Then about 40 years later, a Swede by the name of Svante Arrhenius came along, and he was the first one who actually did a set of calculations that looked at the quantities of greenhouse gases that were in the atmosphere, and he observed that the amount of greenhouse gas that was around the Earth and its atmosphere was sufficient to have an effect on our climate. And as I said a minute ago, that's a good thing. That's why we had warming that made it put us at tolerable temperatures rather than being at 0 degrees Fahrenheit. Then nearly 40 years later, an Englishman by the name of Guy Stewart Callendar came along, and he took Arrhenius's line of thinking and carried it a step further. And he said, well, if greenhouse gases have some effect on the climate of the Earth, then if we're burning fossil fuels and we're adding greenhouse gases to the atmosphere, then maybe it's possible that things that man is doing could actually have an impact on the climate. As a colleague of mine put it to me in a comment a couple of days ago, Earth has been capturing carbon for hundreds of millions of years. We've been in the process of trying to burn all those fossil fuels and release all that carbon in about 200 years. Surely that's not a good idea. So Callendar did an initial set of calculations. He estimated that burning fossil fuels, adding greenhouse gases to the atmosphere could in fact affect the climate. And that's where things stood for a while. There were a couple of problems. First of all, science lives or dies on data. It's great that Callendar had a theory. It's great that Arrhenius had a theory, but neither of them had data. None of them had actual measurements, either of the carbon dioxide in the atmosphere or of changes in climate. So this was a little speculative at the time. Next problem was that not everybody in the scientific community bought into Callendar's ideas. There were others that said, well, yeah, we're releasing a lot of carbon dioxide into the atmosphere, but it'll all be absorbed by the oceans. It won't build up in the atmosphere. And the final stumbling block was they really didn't have good calculational tools at that time to really analyze the problem. So that's where things sort of stalled in the late 1930s. And nothing really happened until about 20 years later, when along came a guy by the name of David Keeling at Scripps Institution of Oceanography. Keeling was not particularly interested in exploring climate change. He just thought carbon dioxide and the way it behaves in the atmosphere was an interesting scientific problem, and he started studying it. And to study it, he put a sensor to measure carbon dioxide on top of Mauna Loa in Hawaii, and just started measuring carbon dioxide in the atmosphere day by day, year in and year out. And this is a plot of the data that he started acquiring back in the late 1950s and how it has changed over the intervening 65 years. And you see two things about it. And both of these things became apparent almost immediately. Within the first 3 or 4 years after Keeling started making measurements, he and the rest of the scientific community saw two things. First of all, they saw those rapid cyclic up and down that you see of carbon dioxide varying in the atmosphere with the seasons. It builds up through part of the year and then decays away through part of the year. But the second thing they saw was that smoothing across those ripples, the overall curve seemed to be generally starting to move up. And that was the real aha moment for the scientific community. That's when people stopped and said, wait a minute, there might really be something here that we need to look at. And they immediately started making estimates of what the impact could be on climate. And because of that early interest, it's actually at about that time, roughly 1965, I don't recall the exact year, that the first presidential briefing on climate change was given. President Lyndon Baines Johnson received a briefing on the possibility of climate change due to increased concentrations of greenhouse gases in the atmosphere back in the mid-60s. So we sort of understood the basic outlines of the problem back then, back in the early 1960s. And everything since then has been trying to understand the details. The scientific community, of course, as they started looking at this, said, well, how can we understand what the impact is going to be? And one of the first things they said is, well, can we look in the past and see what has happened in the past? And will that give us some clues to what might happen in the future? Well, prior to 1958 or so, there hadn't been a David Keeling, but being creative types, they began to find other ways to estimate or measure what carbon dioxide had been in the atmosphere through the previous years. And a lot of different methods have been employed by the scientific community, but one of the most popular and the most effective has been to drill ice cores in the ice of the Antarctic and of Greenland. And as year by year layers of snow and ice build up, they can drill into that and pull out a core of that ice and sample what the carbon dioxide was, and also make estimates of other things like what global temperatures were at the time. And what has come out of that is data of the sort that you see here. What you see on this slide is, excuse me, I lost my laser pointer. What you see on this slide is carbon dioxide concentrations in the atmosphere versus time for the last 800,000 years. The curve that I showed you on the previous slide, that was just looking at the last 60 years or so, all shows up as this virtually a vertical line over at the right-hand side. And so what they've seen is that carbon dioxide levels are higher now than they have been any time in over 800,000 years. And in fact, they're higher than they've been any time in the last 3 to 5 million years. And at that time, 3 to 5 million years ago, there was no ice on the ice caps. Temperatures were 5 to 7 degrees warmer than they are today, up to 18 degrees warmer at the poles. And sea levels were as much as 130 feet higher than they are today. This kind of work has been illuminating and informing what has happened in the past, and it's been an important tool in understanding how climate can change. But this combination of very high atmospheric greenhouse gas levels and the climate that we have today is an unusual combination. We've made a change that's really fast. And so we're doing an experiment with the Earth, and it's not exactly clear how that experiment is going to play out. I'm concentrating on carbon dioxide because it's the primary contributor to greenhouse warming. There are other greenhouse gases as well. I'm not going to talk about them as much tonight, mostly in the interests of time. But just for completeness, I do want to mention them. It's a little challenging for the scientific community to compare what the impact of different greenhouse gases is. First of all, because different gases have different levels of absorption of heat, but they also stay in the atmosphere for different lengths of time. And all that has to be taken into account. But when you do take it into account, you see that you learn that around 2/3 of the global warming that we're seeing comes from carbon dioxide. And about 1/6 comes from methane. Little under 1/6 comes from fluorinated gases like chlorofluorocarbons and hydrofluorocarbons, which are the refrigerants that you find in your refrigerator, your air conditioner. And it's the reason why when you take an air conditioner or a refrigerator out of service, you're asked to take it in for recycling so that those refrigerants can be captured and are not released into the atmosphere. Those gases in the atmosphere do just what that greenhouse from the earlier slide would have done. They capture energy, they warm the Earth system, and the amount of energy that's being added to the Earth system is substantial. It's roughly the equivalent of 5 Hiroshima-sized atomic bombs going off every second. So it's a lot of energy is being added to the Earth system. Most of that energy, more than 90%, goes into warming the oceans, and only about 2% of it goes into warming the atmosphere. And that's probably the major effect that has allowed us to make the changes that we've made to the atmosphere without seeing more dramatic impacts. What is that the oceans have been soaking up a lot of that heat, and so we're not seeing yet as large of effects as we could be seeing in the atmosphere, but that will change. We're already seeing, however, changes in the global temperatures on Earth. This is a picture of how temperatures have changed over the last 60 years or so, since between the sort of mid to late 20th century and today. What kind of changes have we seen? And looking at averages, looking at, for example, the period from 2011 to 2020, that decade, we've already seen global surface temperatures rise by about 2 degrees Fahrenheit from where they were in pre-industrial levels. And quoting from one of the most recent IPCC reports, human activities, principally through emissions of greenhouse gases, have unequivocally caused global warming. I can't even begin to tell you how hard it is to get a group of scientists in a room together and get them to use words like unequivocal. So when they have that level of confidence among a group of scientists who are all looking at the problem from different points of view and different data sets, it's a really compelling result. Even so, you might look at this and say, what's the big deal? You know, we're talking about 2, 3, 4 degrees change in temperature. We see bigger swings than that in the temperature every day. You know, why does that matter? And there are a bunch of reasons why it matters. The first reason, which is probably the hardest one for me to explain, is that we're talking about fairly small changes, but they're changes in the average temperature of the Earth. And small changes in the average can translate into big changes in the likelihood of unusual events. And that's the pictures at the lower half of this slide are trying to help explain that. If you look, first of all, at the picture on the left, and imagine that as describing how likely different kinds of climate are. Most of the time, you see sort of average conditions. Occasionally, you'll see some cold weather or some hot weather. And very rarely, you'll see extreme cold or extreme heat. Now imagine, as you look at the panel to the right, if you just took that picture and slid it a little bit to the right, just change the average just by a little bit, then all of a sudden, those extremely unlikely events become fairly likely. And we're seeing that already. And the converse is also true on the cold side. The extremely unlikely events become even more unlikely. And that's the example that actually comes to mind for me. When I moved to Maine 20 years ago, we routinely expected every winter in January, maybe February, we'd get a below zero cold snap. It was pretty normal every year to expect a short period like that. You might recall last winter when we had a cold snap like that, all of a sudden everybody was very surprised and said, this is really unusual. We don't normally get weather like that. So we're seeing those kinds of changes. So that's one of the reasons why small changes are important. Another reason why small changes are important is because ecosystems, and that includes people, civilizations, are very tightly tuned to narrow environmental ranges. This is a graphic from an analysis that was done asking a very narrow and very specific question. It simply looked at, throughout history, what temperatures have been the temperatures where the highest populations of people have tended to live, and how are those temperatures going to shift by 2070 if we see the kinds of changes that are anticipated right now. And that's what's shown here, where there are some areas, particularly through the tropics, but also southern US, for example, that will become much, much less suitable for large population groups than they have typically been in the past. We'll also see areas that will become more suitable. I use this picture with a good deal of hesitation because the scientists that developed it were asking a very specific and very narrowly defined question about population densities and the temperatures where they had lived. But it's awfully easy to misinterpret a picture like this. It's awfully easy to look at it and say, oh, well, there are going to be some bad areas, but there'll be some really good areas, and we can all just sort of migrate north a little bit. This isn't saying that you can do that. And even if we people could do that, changing our industry, changing our agricultural systems, changing the ecosystems that live in those environments, none of that can simply be accommodated by moving north. Another reason I don't like this slide, not that this is the point that the authors were trying to make, but it's prone to misuse. It's awfully easy to look at the regions where you see the best conditions for populations and bring to bear some cultural prejudices that often come into play, that somehow the civilizations that developed in mid-latitudes are somehow better than other civilizations. So the point is, the science behind this is good, but you have to be really careful not to misinterpret it and not to impute more information to it than it's really trying to say. Another reason why small changes are important has to do with the fact that we've been very fortunate to grow our civilizations in a very benign, stable environment. If you look down at the lower right, this is a plot of temperatures, as it happens, they're from central Greenland, because that's where the ice core data was, but temperatures for the last 100,000 years in central Greenland. And the thing that I want to call your attention to is over here on the right. Since the last ice age, for the last 11,000 or 12,000 years, we've been in this very stable climate. And that's not the way the world has been through most of its life. Even looking back this last 100,000 years, we see it's not uncommon to see big changes, what the scientific community refers to as abrupt climate change, where we've seen big changes as much as 16 degrees centigrade, nearly 30 degrees Fahrenheit, in periods of just years or decades. And the concern is we don't know exactly what triggers that. We don't know exactly why it's been so stable for the last 12,000 years. We don't know exactly what it would take to push us out of that into these kinds of rapid climate change situations. That's an area of very active research. but it's important. As I said, this is what's allowed our civilizations to grow. It's what allowed agriculture to emerge. It's what allowed all the great civilizations to grow. Did any of you see the Ken Burns thing on Buffalo in the last week or two? Okay, you might recall that they pointed out in that the culture that revolved around Buffalo emerged about 10,000 years ago. That's what allowed it to emerge, was that change in conditions.
What is on that y-axis? What is the measurement there?
It's temperature. It's an odd measure. It's a delta temperature. It's not an exact number. Actually, it's on the right here. It's the changes in temperature. So here we're seeing a very stable temperature. Here we're seeing swings of 15 or 20 degrees centigrade.
And then the per mil on the left.
I'm not even sure what that one is offhand. That has to do with the measurements that were being made on the ice core, but I'm focusing for our purposes here just on the temperature scale. Yeah, sure. Another issue is that as we see changes, everything doesn't necessarily change smoothly and gradually. There are a variety of tipping points can be reached where you'll reach a point in changes in climate where it causes or enables something to happen, quite often something that you'd rather not have happen. This particular researcher is doing a survey trying to talk about all the different tipping points that they could think of. For our purposes this evening, I'm just going to mention 3 of them. One is if the ice sheets in the Antarctic or in Greenland were to collapse, that is, if they were to melt, that would lead to sea level rises on the order of 190 to 220 feet. And there's no indication that that's going to happen tomorrow. All of the estimates are that if it happens, it would happen over something on the order of a couple of 100 years. But all of the indications in the research are also that we're moving faster toward collapse of those ice sheets than earlier estimates have been. A second issue that's really troubling is the subarctic regions in Asia and in North America. Those subarctic regions are characterized by massive amounts of permafrost. That permafrost in turn has a huge amount of methane locked up in it. If that permafrost begins to melt and the methane is released, it'll dramatically accelerate warming. The third that I'll mention is changes in ocean currents, changes in the current systems that flow throughout the world's oceans. You're all familiar with the Gulf Stream. The Gulf Stream is part of a larger system that the oceanographic community refers to as the Atlantic Meridional Overturning Circulation. It in turn interacts with other currents, things like currents coming out of the Labrador Sea. If those change their behavior, if the circulation that we've always seen in the Gulf Stream changes, that could lead to fairly dramatic changes in climate. So that's an important example. So there are a lot of these kinds of effects that are of concern. So what does all this add up to? Well, to talk about what it adds up to, we have to look into the future. We don't have a crystal ball, but we do have a set of models that can be used. They're computer models. We have massive models that run on some supercomputers that are used to analyze climate and to predict what the changes might be in the future. But as the research community has developed those models, there are a couple of basic ideas about them that are worth sharing and worth keeping in mind. One is you have to model all the key effects. It might seem sort of obvious, but you have to model all the important things that might be affecting climate. And that's something that the climate research community has understood for decades at this point. I realize that these charts that I put here are going to be a little difficult for you to read, but I put them in just because I wanted to make a couple of points with them. The first point I wanted to make is the chart on the left is from a paper that was done by Jim Hansen at NASA back in 1981. This was one of the first papers that looked at this question of what are all these different effects? How do we sort out what's going on with greenhouse gases from other things that might be happening, like volcanic activity or like changes in output of light from the sun or subtle changes in the orbit of the Earth around the sun. He did some initial estimates looking at those issues. And he was looking again at changes in temperature. The dotted line, which you'll see repeated 3 times, it's exactly the same line, is actual measurements from 1880 to 1970 or so. And he saw right away that increasing greenhouse gas concentrations were going to lead to a steadily increasing trend, increasing temperatures. But it didn't exactly fit the details of what we had seen in the past. Then he added in volcanic activity and it started to fit better. And then he added in solar activity and it fit even better still. That line of thinking, that line of reasoning has continued for the last 4 decades in the scientific community, and they've gotten much more sophisticated about doing those fundamentally those same kinds of calculations. The picture on the right is a picture from the most recent IPCC report in 2021. The black line is essentially the same thing as the dotted line over here. It's what we've observed, what we've actually measured. The brown line is what if we simulate all of the human as well as the natural, like volcanic and solar effects. And you see there's a very good match, very good agreement. Whereas if we simulate only the natural stuff, only solar activity, volcanoes, it just continues kind of roughly no significant change. Lots of little wiggles up and down, but fundamentally it's just going along at the same level. This kind of work has gotten so sophisticated that a whole branch of climate science has grown up around it that's called attribution science. That's all about attributing effects that we're seeing to particular causes and to attributing when we see a single event, like a single storm or a single warm day, is that attributable to climate change? One of the reasons I asked you to put up with me showing you these difficult to read plots is because there's also an issue that comes up repeatedly if you read any of the climate denial literature. One of the things they'll often say, I've seen this in many, many books and reports, is they'll say, well, they don't tell you that between 1940 and 1965, temperatures were actually decreasing. And well, here it is in that data that Hansen used. Between 1940 and 1965, temperatures were just decreasing. That was largely due to volcanic and solar activity. That doesn't change the basic idea that if you don't cherry pick and don't look just at that little time period, but instead look at the longer term, the overall trend is upwards. They'll also say, they don't tell you about these other effects like solar activity and volcanoes. And well, they do tell you. Here it is. It's been in the literature for over 40 years. It's repeated time and time again in the literature. But this mythology lives on that somehow climate scientists are not thinking about these issues, which to them are pretty obvious issues, and they know they need to consider. Another point that's related to this idea of looking at all the key effects is you have to adopt a global view. You have to look at the whole world. You can't look at just a little piece of it. Has anybody here ever heard of John Ruskin? To the extent anybody remembers John Ruskin today, they usually remember him as sort of an eccentric art critic that picked a fight with Whistler. But he was a whole lot more than that. And today, we'd probably call him a Renaissance man. He had a lot of interesting ideas on a lot of things. And one of the things that he contributed to is the very beginnings of the whole climate science and meteorology community, where he said the meteorological society wishes to be a vast machine. It wishes to know at any given instant the state of the atmosphere on every point on the globe. The picture on the right is a picture from about 20 years after that was developed by an oceanographer by the name of Matthew Fontaine Maury, with his ideas about how climate and specifically air circulation worked on the globe as a whole. One of the things I find interesting about this is the fact that these ideas started emerging in the middle of the 19th century. And the reason they started to emerge at that time was because of the emergence of the telegraph. Because all of a sudden, it was possible to share information all over the world and to know within minutes what the weather was like anywhere in the world. So that really enabled people to start to develop this kind of a global view. But this basic idea of knowing at any given instant the state of the atmosphere on every point on the globe, if we fast forward to today, is exactly the basis behind all those models that I talked about that are now run on supercomputers. You see the cartoon on the right here that has the Earth superimposed with sort of a checkerboard grid. It's very much that idea. In each little cell on the grid, understanding exactly what the conditions are and understanding how that cell will interact with the cell next to it. I'm not going to dwell on the details. That's what the picture on the left is all about, is just showing a progression over time about how the scientific community has steadily added complexity to these models and added more and more details to them. So they're trying to model the entire globe, but they're also trying to get a whole lot of specific details right. So what have we learned from these kinds of models? Well, here in Maine, we know one of the things we've learned is that climate's going to change. And this is a picture that I took from a DACF, a State of Maine publication that tries to graphically suggest what changes in climate might be in Maine. If the world continues business as usual without getting greenhouse gas emissions under control, by late in this century, we can expect here in mid-coast Maine to see climate sort of like what we would have thought of as Chesapeake Bay Area. Even if we manage to get emissions under control sufficient to meet the kinds of goals you hear about in the news, like limiting warming to 1.5 or 2 degrees C, we're still going to see changes in climate. A certain amount of warming is already baked into the system. And we're going to see changes that will give us climate that might be akin to Long Island or the New Jersey shore. So we're going to see some changes in Maine. One of the changes we'll see is sea level rise. I'm not going to dwell on this. Some of you, I think, were here in October when we presented the vulnerability assessment that City of Bath has just had done on sea level rise, but that'll be one of the impacts. There are a lot of other impacts. Let me touch on just a few of them. I know this is, we had to go to an alternate projector tonight, and I know this is a little hard for many of you to read. I've talked about sea level rise. I've talked about weather extremes. We're going to see changes in air quality, and that'll include things like forest fires. Remember all the forest fires in Canada this summer? We'll see human migrations. Do you remember a few years ago during the fighting in Syria when something like 2 or 3 million Syrian refugees descended on Europe? You remember how much turmoil that caused in Europe? 2 or 3 million refugees. The World Bank is estimating that by mid-century, we're going to see climate-driven refugees in the numbers of the hundreds of millions on Earth. And so we think about how we're going to deal with that. Well, similarly, we'll see wildlife attempting to migrate where they can't migrate. They'll be faced with others that are invading their area that are trying to migrate. We'll see extinctions. Just a single example to perhaps drive this home for you. Moose in Maine. Moose don't have any natural defenses for ticks. They don't switch their tails to drive them away. They don't groom one another. They're very solitary animals. But that's been okay because they're cold weather animals. And they have evolved to live in a climate where it gets cold enough that the ticks are all killed off in the winter. Well, we're starting to have mild winters and the ticks are not getting killed off. I've seen photographs of individual moose that were literally bled to death by tens of thousands of ticks infesting their bodies. Those are the kinds of things that can happen. Oceans are warming. I told you earlier, 90% of the warming that has energy that has been produced by warming from excess greenhouse gases has gone into warming the oceans. Also, I told you that there was debate early on about how much of those greenhouse gases like carbon dioxide would be absorbed by the ocean and how much would stay in the atmosphere. The answer is it ends up somewhere in the middle. Roughly 31% of the carbon dioxide that has been released from fossil fuel emissions has been absorbed in the oceans. Unfortunately, once it's absorbed in the oceans, it doesn't stay as carbon dioxide. It undergoes a chemical reaction and a significant portion of it converts to carbonic acid. And that's reducing the overall, increasing rather, the overall acidity levels of the ocean. Oceans are about 30% more acidic now than they were in pre-industrial days. That's tough on a lot of the critters in the oceans. It's particularly tough on shellfish, lobsters, clams, mussels, so on. Water quality is an issue. You're probably, any of you who might live in the peninsulas in Harpswell and Phippsburg, Georgetown, Arousik, you're all hearing concerns about saltwater intrusion in your wells. That is an issue and will become more an issue. Variety of disease and pandemic issues come up. Just a single example of a disease issue. There are documented cases of reindeer in those subarctic permafrost regions that I talked about that were buried over 100 years ago because they had died and were infected with anthrax. Some of those bodies are now thawing out, and there are documented cases of the anthrax being released and causing cases in the population of anthrax. That's just one of the many examples of the kinds of things that can happen. And then there'll be a whole set of economic issues, heating and cooling costs, fisheries and agriculture, tourism, recreation, what have you. So if that all doesn't sound bad enough, it actually gets a little bit worse. People of my generation learned about ecology from Barry Commoner. He's thought of as the father of modern ecology. And Commoner's first law is everything is connected with everything else. And so all those things I was talking about on the previous slide, researchers are trying to understand how do they interact with each other? How will one of those things affect some other thing that's happening? And what will it all lead to? what's the end game here? How does all this fit together? So all that's by way of saying that we have a pretty good understanding of the science behind climate change at this point. That's really what this talk was all about, but I'd be remiss if I didn't talk at least a little bit about what we can do about it. So in the remaining few minutes, I'll take just a few minutes to talk about what we can do about it, and then we'll take some questions.
Here, I've got an experiment for you. Safety glasses on. By the end of this century, if emissions keep rising, the average temperature on Earth could go up another 4 to 8 degrees. There are a lot of things we can put it out. Are any of them free? Well, of course not. We're not children anymore. I didn't mind explaining photosynthesis to you when you were 12, but you're adults now, and this is an actual crisis. Got it?
I just thought Bill Nye said it a lot better than I could. So what is it we need to do? Several things. First of all, we just need to stop the emissions of greenhouse gases that we're doing. And as I haven't dwelled on it, but as I showed you on one slide, it's not just CO2, it's also methane, the nitrous oxides, the HFCs, and so on. We need to just stop. And not only do we need to stop, we know that there's a significant amount of warming already built into the system from the gases that have already been released. So we need to work on capturing some of that CO2 and actually taking it out of the atmosphere. The technical term is sequestration. My personal opinion is that a good target for us, if you happen to be interested in numerical values, would be to get atmospheric CO2 levels back to where they were early in the 20th century, which is at a level of about 300 parts per million. We've raised them up for 40% above that at this point. We're at about 420 parts per million at this point. So that's the first thing that needs to happen. But we're also going to have to remediate and adapt. As I keep saying, a certain amount of warming is already built into the system. We're going to have to respond to those effects, and we're going to have to look forward to some changes. Some of them will be disruptive. Many of them will be transformational, not in a bad way. Some of them can be in a very good way. There's a lot of opportunity here. This is a plot from the most recent IPCC report this past summer in 2023, where they said limiting warming to something in the neighborhood of 1.5 to 2 degrees centigrade involves rapid, deep, and in most cases, immediate greenhouse gas emission reductions. Let me talk a little bit about what they mean when they say that. There's a lot of information on this slide, this picture, that I'll try to talk you through it. What you're seeing here is the quantity of greenhouse gases emitted annually versus time in years. And it's measured in what are called CO2 equivalents. It's that idea that I was suggesting to you when I showed you the other greenhouse gases, that we can sort out how to compare them to the effect CO2 would have. And what we've been seeing is, first of all, the black line is what's been happening for the last 15 or 20 years, steady increases in the amount of greenhouse gases that are emitted. The second thing that you see on this slide is, if you look at the policies that the countries of the world have actually implemented, not what they've promised, not what they've talked about, but what they have actually implemented, that's what the red line is. And it has this slightly increasing, but for the most part, sort of leveling off in the level of greenhouse gas emissions, but at a pretty high level, up around 60 gigatons equivalent per year. That level of greenhouse gases would lead to warming of estimated to be around 3.2 degrees centigrade. The brownish and the bluish line are if we want to limit warming to 2 degrees C or 1.5 degrees C. would require an almost immediate and very steep fall off in the amount of greenhouse gases that are being emitted. That's what IPCC meant when they said rapid, deep, and in most cases immediate. You often hear numbers set for goals. We've set one in the state of Maine. We've set one here in the city of Bath as well, that are typically numbers like 80% reduction by 2050. This picture is where those kinds of numbers come from. Right now, we're in the neighborhood of 50 gigatons per year. By 2050, if we want to get down to 1.5 to 2 degrees C, we need to get those emissions down to about 10 gigatons per year instead of 50. So that's an 80% reduction. So how do I square that with the fact that on the previous slide, I said, we just need to stop? Well, the reason is because 80% is a fine goal, but you have to recognize not everybody's going to be able to do it. Some countries are going to be too poor to do it. They're too busy trying to feed and clothe their people to work on greenhouse gas reductions. Others are just not going to be able to marshal the political will. So there's lots of reasons why not everybody will achieve 80. But if nobody achieves more than 80 to help 80% reduction, to help counterbalance that, then you know that in total, we're just not going to get where we need to be. So anybody that can do it needs to move as close as they can to just eliminating greenhouse gas reductions, greenhouse gas emissions. So what can you do? The first thing I'd say is, even though I know I've given you a real doom and gloom kind of a talk, don't get discouraged. I mean, the thing that is fascinating to me about this problem is that we understand it. We know what it is we need to do. Marshaling the will to do it, figuring out exactly how to implement it, all of those things are hard, but we know what we need to do. You know, we don't have to feel confused and uncertain about that. Take individual actions. Do the things you can do in your own life to reduce your own, as the saying goes, carbon footprint. Reduce your own emissions. And in so doing, demonstrate by leadership for your neighbors. Encourage societal action. One of the things that troubles me, I'm a technical guy, and the technical stuff I've got my arms around. I feel like I understand. The political stuff, not so much. But one of the things that troubles me is when I see surveys, I see that virtually everybody is concerned about climate change, but very few people say it's an issue that I vote on. It's the issue that drives my decisions at the ballot box. And that, I believe, needs to change. You know, we need to encourage societal action. We need to deliver the message to our leaders, to our politicians, that we're expecting them to act on all of this. But let me talk about the individual action stuff just a little bit more. And I'll use transportation as an example. I could have used your home or your school or your business, but I didn't. I used transportation. There's a lot of things you can do. And the message that I'd like to convey to you is we need to make some big changes. But you don't have to go home and make it tonight. You don't have to run out and buy an electric car tomorrow. So, but I'd have, if it was me, I'd have a plan, and I do, for when am I going to buy an electric car? But in the meantime, what can you do? You can drive less, you can bicycle more, maybe think about ride sharing, maybe get an electric bike. If you've got an old gas guzzler, what can you do about that? You know, at the very least, get a car that's more efficient, maybe get a hybrid. Maybe you're not ready to get an electric car until the infrastructure catches up and until the prices come down. That's okay. There's lots of things you can do. And the thing that I see when I look at all these things on there is there's nothing on there that says we have to suffer. You know, nothing that says that, you know, we have to really give up things that we value in our lifestyle. It's just a matter of doing things differently. And there are some, as I said, I could have done a similar picture for your home, your school, your business. I didn't. One of the reasons I didn't is because it gave me a good opportunity to put this up, which is just a reminder of our schedule coming up. We don't have a climate conversation scheduled for December, but we do have them in January and March and April, mostly focused on things you can do around your house. So I hope you'll be interested in participating in those. The other thing that I should mention and make you aware of is the city is in the process of evaluating proposals and ultimately hiring a consultant who will be developing a climate action plan, an updated climate action plan for the city. We did one in 2019. It badly needs update. We're going to be working through that, and quite separate from these climate conversations events. Stay tuned. You'll hear more about public opportunities to engage and be involved in those climate conversations. With that, let me wrap this up and take any questions you might have. Rod, do you want to see if we can get the lights?
Yeah. Can we also mention, John, to the folks on Zoom that they can write in the Q&A?
Oh, yes, absolutely. I'm sorry. I'm sorry.
Yeah.
Yes, by all means, those on Zoom, you're welcome to submit questions as well. Put them in the Q&A. Rod will be monitoring those and let me know as any questions come up. Yes.
Yeah, John, I want to start by just commending you for definitely a comprehensive overview of the science.
Okay, thank you.
You did a very good job there. You mentioned voting, and people don't vote based upon things like climate change.
Mm-hmm.
And yet I would say that given the number of billion-dollar disasters that we have every year and that are escalating over time, that is certainly an economic issue. And we know that a lot of that is attributable to the climate change. So I would say that, you know, there is a way that you can approach that subject from an economic standpoint.
Right.
Another economic issue is this balance that you mentioned between mitigation and adaptation.
Mm-hmm.
I think we know fairly certainly that as time goes on, the ability to adapt to climate change is going to become more and more difficult.
Mm-hmm.
We're just not going to be able to approach the consequences of climate change in a truly wholly constructive way. I mean, you look at Paradise, California, you look at the recent fires in Hawaii, you look at the retreat of various towns from the coastal areas. Those are supremely expensive endeavors, which will never be fully accomplished. You'll never fully be able to reconstitute, you know, the town of Paradise or the town of Lanai in Hawaii.
Yep.
So I think intrinsically there are some really core economic issues if we could find a way to communicate.
You're absolutely right. That sort of education is critically important, helping an audience and a community understand that doing nothing is not an option. We're either going to pay the bills needed to get this under control, or we're going to pay the bills to repair the damages. And all of the estimates that I've seen, without exception, say that the bills associated with repairing the damage will be much, much greater than the cost of planning and preparation and getting this under control. So you're quite right. That's a very important part of the discussion. Sure.
It was a great speech. Thanks. It was a great summary. In regards to the Holocene, the 11,000 years, it was really flat and it was very distinct. And you said that it's an active area of research. Do you know, or do you have any knowledge of what the lead hypotheses for what has caused that? Or I'm just really curious about that, 'cause it's very
It is very
distinctive.
it's very distinctive, and I'll confess, the honest answer to your question is no, I don't. It's not an area that I'm familiar with. I don't know the details. I know it's being actively researched. I'm sure there are some ideas out there for what those triggers are and what causes it, but it's not a subject I'm familiar with.
I think I can give you one good cause for that question. And that's the human population. During the Holocene after last ice age, human population is still fairly stable. But in the last several hundred years, the population has increased exponentially.
Mhm.
So, I mean, so you didn't have any graphs of the human population. But if you think of the population, the estimated population throughout known history, all of a sudden you see this almost exponential increase in the numbers of people on the
Mhm.
planet. And billions of people are gonna have
Right.
lots of impact,
Right.
whether it's using resources or producing pollution or whatever it may be.
Right.
But that's just, I just wanted to throw
Right.
that out there.
It's
But you go ahead.
I was to say it's a good point. Certainly, population change is an important factor. What the population change doesn't explain is why it was that 11,700 years ago there was this very dramatic and obvious change in the way climate behaved.
Yeah.
That's not related to
It was
population
flat.
change. It's just all of a sudden it just flattened out. Right. It is weird, and I don't even begin to understand it. Do I have any questions online? Nope.
What I wanted to say, one thing to suggest, is
Yes.
that in terms of mitigation, I think that transportation could be a key one that we here in Bath and in Maine get involved in. And that's
Right.
encouraging public transportation.
Right.
And, you know, like one example, I think, I mean, I don't know all the details, of course, but I think the Maine DOT needs to concentrate
Right.
more on public transportation and less on these
Right.
huge expenditures of highway construction. Not to say we don't need to improve our roads, because that's
Right.
definitely the case. But that's
Right.
just one aspect.
Right.
The other one is, I think here in Bath, one thing we could do is, this is just an idea, is that incorporate the school transportation system into a citywide entity.
Mhm.
For instance, in, you know, large metropolitan areas, they don't have school buses.
Right.
They have bus systems, and the children, the kids, the students use the bus system.
Right.
And perhaps if we had a bus system that incorporated the student, you know, school activity, as well as the local
Right.
population, that might decrease, you know, the use of vehicles.
Right. It's a good point. Take the 2 points
Yeah.
slightly separately. The state of Maine planning at the state level is very focused on the transportation issues. When they did the state of Maine Climate Action Plan back in 2020, was it? The inventory they did of the sources and causes of greenhouse gases, nearly 50% of the state of Maine emissions are associated with transportation. So transportation is a really big issue for the state. Here in Bath, it's not quite that extreme. We're a little more localized, a little more contained. The last inventory we did, it was closer to the neighborhood of 25%. I won't get the number exactly right, but it was around a quarter of our emissions. And so you're right, at the local level, anything we can do, recognize it's not just a matter of converting to electric cars. It's also a matter of future development being done in a way that makes the city more livable, more walkable, more bicycle opportunities. As you said, improved public transit, ideas like merging public transit with school transit is an intriguing idea. That's something that we've got a couple of council members in the room here that I'm glad they're hearing it, give them something to think about.
We do have an online question.
Yes.
And then we'll get into, has anyone shown a picture of what a wealthy nation achieving net zero carbon emissions looks like?
or finances aside, is it even feasible to meet power needs with solar, wind, and nuclear? And anybody can answer.
Okay. I'll take the second half of the question first. Is it feasible, particularly if you're including, as the questioner did, nuclear in the equation, then it's certainly feasible. Taking Maine alone, Maine's electricity supply is actually pretty clean right now. There's a small amount of natural gas fired power generation. There's no coal-fired generation, as far as I know. You do have to decide whether Maine's power generation is completely clean, moves you into a debate about how you feel about biomass and whether biomass is a clean source of energy or not. But if you accept that it is, then Maine has already got pretty clean power. Other states have bigger problems. West Virginia, I don't mean to pick on West Virginia, but I will. I mean, they just happen to be a state for obvious economic reasons that is heavily dependent on coal-fired power. And so the transition costs for them will be higher. But for us here in Maine, we have lots of opportunities, whether it's offshore wind or solar or what your choices might be. Part of the issue, which I know is a lot of what's going on at the state level, is thinking about how to plan for that future energy grid that accommodates all those different sources. And that's something that we've had to make that conscious decision here in Bath, that we work on the part of the problem we can work on, but we're depending on the state to come to the table and provide that flexible grid and the green power. Ruth, you had a question?
No, I guess I was thinking in terms of transportation. I think one thing I've been excited to hear about or to see is just that Bath does now have the Blue Line, which has been like the Blue Line bus, which I think goes between Lewiston and Bath, and I know it's like targeted for specific jobs, but that's an exciting new innovation in Bath through transportation. And the Ed community is talking about building a bicycle pedestrian trail between Brunswick and between the bike path and make it easier for people to move between these communities. And I think the Breeze bus system in Brunswick that goes to Portland, it's been exciting to see that some of these options are starting to come along. And I think it'll be and fun to have conversations going forward.
I agree.
How can we make them how can we make them more useful for people so that they're have a chance to grow more?
Yeah, those are great comments. I really appreciate you pointing that out. And it's very consistent, and you said it in some ways better than I did, but it's very consistent with what I was trying to say when I showed my little cartoon of all the different choices and decisions for transportation. It's to dispel any idea that there's just this one thing that you need to do, and if you just did that one thing, everything would be over. And instead it's a lot of little choices, and just getting into that mindset of saying, what can I do this week to do a little better than I did last week? What can I do that this next year that'll be a little better than what I did this year? And being ready to accommodate those changes and look forward to some of the opportunities that they're going to give. I'm like Ruth. I think these kinds of transportation options are really exciting. Other questions? Yes, Paul.
So thank you, John. That was excellent. You made the comment, don't get discouraged.
Right.
You know, you hear this kind of talk, and part of me is feeling like, yes, let's all make it happen yesterday. Let's address this. But then you talk about that people don't show up at the ballot box and vote on this issue. And we still have people walking around who call it a hoax. So I guess I really don't understand. Are people just not scientifically educated or literate? Are they not paying attention? Do they not want to? But what is it that, in your view, keeps people from embracing this as an urgent issue? It is.
I guess I get outside my box when I try to answer a question like that. It's out of my comfort zone, but I'll take a stab at it anyway. I don't think there's any single answer. I think there are certainly those cases of people that just don't believe it or choose not to believe it. I mean, to me, the science is compelling, so I find it hard to understand that. But there are those cases. Some people just don't have the time. They are wrapped up with their day-to-day challenges of trying to keep their life and their household together and don't have the time to think or worry about this. So I think there's a whole variety of reasons. I think there's, to a degree, it gets exploited for political purposes on either side, and that has to be dealt with. So I think it's largely an education issue, I'd like to believe. It's helping people understand, as I said, that it's not some single dramatic change. You don't have to go out tomorrow and drop $50,000 on an electric car, but it is a lifestyle change. It's helping people get used to something new. Change is hard for everybody. Nobody likes change. But yet, I would venture to guess that everybody in here makes plans for how you're going to get health care. You make plans for how you're going to manage your retirement. You make plans for how you're going to put your kids through school. This is another of those things that is a part of life today. And we all need to learn how to plan for it. It's the best I can do to respond to your question. Yes.
My name is Jean Pizzetti, and one of the things I want to comment on as far as voting for it at the ballot box and systemic change is the influence of corporations and money on systemic change.
Mm-hmm.
One of the most important things I think we need to do as a society is get money out of politics. It's what it is what
Right.
Yeah, it's what subsidizes fossil fuels rather than renewables. It's what, to some extent, and I staffed the Energy and Utilities Committee of the legislature for a few years now. I'm just going to announce now I'm running for Senate in 2024. I have a bachelor's of science in biology, a master's of science in natural resource management. But where I was going to go with this is just for like a basic understanding. When it comes to renewable energy, the reason we don't have, one of the reasons I believe we don't have it on our roofs is because the transmission and distribution utilities don't have to pay, they don't get money for the electricity that's generated on your roof going to the light bulb in your house, right?
Right.
And I was in the legislature 10 years ago as the analyst, and I watched our transmission and distribution utilities vote down every renewable energy bill because they wouldn't make money off of renewable energy. And so it's really kind of pulling that money out of politics so that the changes that the people want happen. I don't really think it's that people don't want the change. I think people do want the change, but the power isn't in the people right now. So things like Fighting Back and Citizens United, things like ranked choice voting, because what that does, I mean, I'm running as a Democrat, but what ranked choice voting does is it allows a third party to come in. And allowing a third party to come in allows for moderation, which allows for compromise. And so I really believe that ultimately the reason we can't get past making change is about individual people. It's about the great corporations. So I just wanted to.
Right. Okay, that's great. I suspect they're trying to kick us out.
Yeah.
It's time for the library to close.
By 6:52.
Okay.
So we'll need to wrap this up. I'm
Yes,
sorry.
that's all right. No, I appreciate it, Ruth. Okay. Thank you. Thank you all for the questions. It was a great discussion.